Organizer for invited me to give this talk. This is my first time to get India. I'm very happy for these days in ICTS. I think ICTS is a very nice place. Okay. My talk is about K groups of number fields. In this talk, I will talk about some results about Tame Kernels and higher class numbers in extensions of number fields. Well, let F be a number field. OF is ring of integers. The problem of computing the hierarchy groups of number field and of its rings of integers OF has a rich history. You can see the reference 1, 4, 5, and 17. Here, I'm not going to talk about the definition of the K groups because the definition is very complicated. I think I can introduce some results about Quadrant. In reference 17, Quadrant proved that for all positive m, the K-series groups Kn/OF are finitely generated. In fact, if n is zero, K0OF is isomorphical to Z plus the class group of OF. That means the Tauschen subgroup of K0OF is the class group of a number field F. And N is 1, K1OF is the unit group of OF. And for M is an even number, KNOF is a finite group. And N is an odd number, KNOF is finitely generated as the module. There are various conjectures about their Tauschen subgroups. One of them, due to Lichtenbaum, says Lichtenbaum Conjecture for all m is greater than or equal to 2, that f star 1 minus m is the plus minus the order of the group K2m minus 2OF over the order of a Tauschen subgroup of K2m minus 1OF times the Borel regulator. The Borel regulator is similar. I think you can think that is a similar regulator of number field. Theta F star 1 minus n is the first non-vanishing coefficient in the Taylor expansion of a theta function. Theta F s at s is 1 minus m. That is the Lichtenbaum Conjecture. Well, for n is 1, there is an exact sequence as follows. 0 maps K2OF, maps K2F, maps KP, the sum of KP star, where KP is the radial field of prime ideal P of OF, where the map tau P is explicitly given by the so-called Tame symbols. For each prime ideal P of OF, the map tau P that from K to F maps Kp star defined by this formula. Well, this K2F can be defined by symbols like this. By the definition of Milnor, K2F is the set like this. Yes, is the symbol. This symbol is the Sternberger symbol. So for every element AB and the image of AB actor tau P is the like this, where Vp denotes the p-adical valuation. So from this exact sequence, K2OF is the kernel of tau P. Hence, the K2OF is also called the Tame kernel. That is the Tame kernel. That means the Tame kernel is the second K-series of rings of integers of number fields. Oh, sorry, F star. So, in classical algebraic number theory, the study of the ideal class group is one of the fundamental problems, like the last one talks in the morning. Okay. The analogue of the class group in the realm of K2 function is the Tame kernel. You know, the class group is a finite group, yeah, and the Tame kernel is also a finite group. So we need to find what is the Tame kernel, but Tame kernel is much more complicated than the class group. That is because the definition of K2 groups is very complicated. So one of the fundamental problems in these areas is the understanding of the P rank of K2OF, of number fields F. Yeah. By the two-rank K2OF formula due to the Birch-Tate, Blocking and Skinner states that for F is a quadratic field, Q the square root of D, where D is in D is square free. The subgroups of K2OF consisting of all elements with order 2 can be generated by this form element minus 1 m, where m divides the D, together with like this form element minus 1 u plus the square root of d if d is the square the square of u minus 2 times the square of w, where uw is an integer. Professor Qin formulation theory determines the 4 rank of K2OF. The same F is the quadratic field, Q the square root of D, and if D is a positive, SD is the set of plus minus 1 and plus minus 2, or if D is a negative, and SD is the set of 1 and 2. Suppose that M divides D, and if D is positive, M is positive. And if 2 is the normal of F, we can write D is the square of U minus 2 square of W, with U, W is in Z. Then this element is of order of 2. If this element is a square of K2OF, if and only if one can find an epsilon in SD such that for any order prime P divides M, the Legendre symbol P over D M minus is equal to the Legendre symbol P over epsilon.
Notation K2OF2 is misleading. You really mean 2 times K2OF, right? This is an abelian group. K2OF is an abelian group.
Yeah, it's an abelian group. Yeah.
So you mean 2 K2OF?
Yeah.
Yeah?
Yeah. Yeah. And like this element is order of 2 is the square of K2OF. If and only if one can find a data in SD such that for any order prime P divides M, this Legendre symbol P over dm minus 1 is equal to this Legendre symbol. For any order prime P divides the dm minus 1, this Legendre symbol P over M is equal to this Legendre symbol. So this result is very clear. So indeed, Professor Qin introduced the sign matrix via Legendre symbols to determine the 4 rank of K2OF, where F is the quadratic extension in theory 1.1 above. You can see the reference 192012. In the case of a relative quadratic extension, the sign matrix defined where local Hilbert symbols to compute the 4 rank of the Tame kernel was the work of the Harry Brink and Coster. In reference 14 and 13, Professor Qin also determined the 8 rank of K2OF completely. Yeah, this is about 2 ranks of Tame kernels. For any order prime P, this is very different from the 2 because every number field that contains the contains the roots of unity of order 2, but doesn't always contain the p roots of unity. So for any order prime p, we shall consider the following short elect sequence. This sequence is about a relation between the Tame kernels and the class group. Yeah. Where UP is the group of P of P's roots of a unit, and the CLOE 1 over P is the P class group. Where E is a number field F theta P. Theta P is the primitive P's root of unit. And G is the Galois group, E over F. And G acts on this group by the formula. And it acts on this group is by diagonal. And the S prime is the set of prime ideas of F which divide P and split completely in E. So, based on appropriate reflection theories and on the above elect sequence, some authors proved several results connecting the P-rank K2OF with the P-rank of the class group of K, where K is an appropriate subfield of F theta P. In the case of correct fields and cubic fields, P is 3 or 5. The results are explicit. You can see the reference to 21, 16, and 15. In 2010, Professor Tim proved the reflection theory, which for P is 3 is x to 3 is a Scholz reflection theorem. He obtained some formula for the PM rank of the K2OF. With the help of this reflection theory, he established relations between the Pn divisibility of the order of K2OF and the PM divisibility of the class number of some algebra number fields. Yeah. Okay. About the extension, a Galois extension of number field, we started the structure of the odd part of the Tame kernel K2OF of F by using the intermediate fields of F over K. Yeah. Some results is the following. That F over K be an abelian extension with a Galois group G of order M, and M doesn't divide M, P doesn't divide M, then the P0 subgroup of K2OF is the sum the P0 subgroup of the K2OE. Well, where E runs over all intermediate fields cyclic over K. Just the cyclic. From this, this result is about the abelian extension. If F is a multi-correct field, where D1 and Dn are square-free integers, and G is the Galois group F over Q. So this is the degree is the 2 power m. So if P is an order prime, then the P0 subgroup over K2OF is the direct sum of the P0 subgroup K2OE, where E runs over all correct subfields over EF of F. So by this result, we can compute Tame Kernels about this multi-quadratic field, because that is in the random Birch-Tate conjecture. The Birch-Tate conjecture is the special case of Lichtenbaum Conjecture. That is, the number of Tame Kernels is equal to W2F and ZF minus 1, the value. Birch-Tate conjecture is for every totally real number field. Just for every totally real number field, where ZF is the Dedekind Z function of F, and W2F is the maximal order of the roots of unity, belongs to the compositum of all quadratic extensions of F. This can be W2F can be computed. The conjecture is known to be true where F is abelian over Q, and is known to be true in general up to a power of 2. So, by proposition 1.3, the order of the group K2OF can be computed for a real multi-quadratic field. So, we compute some many fields like this. Okay. How about the non-abelian group, non-abelian extension of number fields? Let E over F will be a finite extension of number fields. The transfer was defined, which is a group homomorphism. The transfer is from K2E to K2F. Using some basic properties of the transfer mapping in K-theory, we proved some relations among the orders of all parts of Tame Kernels of some subfields of E over F. we denote it by K2 E over F is the corner of the map transfer. But this transfer is the restriction on the K2OE from K2OE to K2OF. By the property of a transfer map, we can prove that this result, let L be an order prime number and the E over F be a dihedral extension with a Galois group DL. This DL is generated by sigma and tau. K is a quadratic subfield fixed by sigma. The small k. The big K is the fixed field of tau, and the big K prime, the fixed field of sigma tau. Then, for every order prime, P is not L. We have this isomorphism. E over K2 E over K, P, that means the P zero subgroup of this group is isomorphic to the product. And about the order of Tame Kernels is this formula. That is K2 OE, the order of the K2 OE times the order of the K2 OF, the square, is equal to the order of the K2 OK square and times the order of K2O small k for P factor. Just for P factor, P is not L. So if you that F is Q, you can compute the Tame kernel, the number of the Tame kernel of E by this equation, by this formula. Okay. Next, we will talk about higher class numbers in extension of number fields. It is known that one has the analytic class number formula. This is well known. ZF star 0 is the minus R1F times HF over W1F, where W1F is the number of roots of unity in F. HF is the class number of F. R1F is the first regulator of F. And the ZF star 0 is the first non-vanishing coefficient in Taylor expansion of the theta function ZF around S is equal to 0. And the conjecture in K-series, the conjecture analogous of this formula when 0 is replaced by negative integers. Like this conjecture. This conjecture is the Lichtenbaum Conjecture material formulation. Yeah. For any number field F, And for any integer m is greater than and or equal to 2, this value is equal to plus minus this number. And this H and F is the higher class number. That is the order of the Motivic cohomology group. The Motivic cohomology group is very complicated, but it is abelian finite group. W and F is the order of the torsion subgroup of the Motivic cohomological group HM1. And this Motivic cohomology group is finitely generated as the Z module, but it is not finite. So R and MF is the Motivic regulator of HM1 OF ZM. Oh, the same as before, you know, that's the non-vanishing coefficient of the theta, yeah. The same, yeah. You know, for all n, Motivic groups is also complicated. We just know their abelian group, and for m is greater than or equal to 2, the Motivic groups HM2 are finite, and the HM1 are finite generated Z module, and its rank is equal if n is order, and this n, if n is order, its rank is R1 plus R2. If n is even, its rank is R2, where R1 and R2 are respectively the numbers of the real and the complex place of F. So, but material cohomology, ETL cohomology, and K-series K groups, the definition is very, very complicated, but relationship is clear. Is described where 10 characters. That's me. This result. That OF will be the ring of the integers in a number field F with R1 dual impedance, and that n is greater than and or equal to 2. Then for I is the 1 or 2. The 10 character, if 2 times n minus 1 equivalent to 0, 1, 2, 7, model 8. The 10 character is the isomorphism between the K groups and the homological, Motivic homological group, cohomological group. If 2n minus I is the equivalent 6, model 8, the 10 character is injective between the two groups. And with a co-corner is an isomorphism, this group. And if 2 times n minus 1, minus I equivalent to 3, module 8, the 10 character between the two groups is surjective with the kernel is isomorphic to this group. If n is equivalent 3 module 4, there is an eclectic sequence. This sequence is between K groups and these cohomological groups. And for all primes P, the material cohomological group is isomorphic, tensor P is isomorphic to this ethyl cohomological group. Yeah, these are famous results. It's about relation between the three complicated group. Well, we know in classical number theory, some authors studied the relation about the class number in extension of number field. So we can also start the relation about the higher class number in extension of number field. So let F be a finite Galois extension of a number field K with the Galois groups broad and plot independently some multiplicative relations between the Dedekind theta functions of some subgroups F. Like this, for every cyclic subgroup H over G, CGH is this number. Where H star is a cyclic containing between the two, is a cyclic subgroup between the group H and G, where mu is the Mobius function. Then, in this Galois extension, there are formula about theta, Dedekind theta function like this. Theta Ks is equal to the product of this theta function, where Fh is the subfield of F fixed by H. H is the subgroup of G. G is the F over K. G is the Galois group F over K. So we just started the extension of number field of order 2L and 4. Let L be a prime number and D is the dihedral group of order 2L. And let F over Q be a complex Galois extension with the Galois group G, where G is the Klein group of order 4 or D. When n is even, we give the Brown-Kluder formula for higher class numbers by an index of the first material cohomology groups using the Brown-Kluder relations about the theta functions. And the Motivic formulation of the Lichtenbaum conjecture. That means we need to assume the Motivic formulation of the Lichtenbaum conjecture. If we assume this conjecture and we use the broad product relation about that function, we can get this results. Let F be a complex by quadratic extension of Q with a quadratic subfields F0, F1, and F2. Where F0 is real, because the F will be a complex extension. Then for n is greater than 1, we have this equation. This equation is HNF is the higher class number of F. HNQ is the higher class number of Q. And HNFI is the higher class number of Fi. This equation is equal to 1 or 2 or 1/2. That is the Galois group is the Klein group of order 4. Yeah. Let F will be a complex Galois extension of Q with the dihedral Galois group DL. Let K be the unique quadratic subgroup of F, and K the subfield of F fixed by sigma, and K prime the subfield of F fixed by the square of tau times sigma. Then, if L is equal to 3, we have this formula. You know, in this extension, there have 4 number fields. The 4 number fields, the higher class numbers of the 4 number fields, the relation is here. The equation is equal 1/3 or 1 or 9 or 3. Just the 4 possible values. But by the relationship K group and the Motivic cohomology group, we can get this corollary. That K is the pure number field of degree 3, and the F is the K theta 3, where M is the cube free integers not equal 1 and -1. Theta 3 is the primitive cube root of unit. Then this order of the Tame Kernels is equal to this. The 4 possible case. The 4 possible case about the Tame kernel of OK. Yeah. So this is from this you know. Sorry. This equation, this formula just for P is not L. P is not L, but the last result is is contained in P. This result is for all primary number. P is equal to 3. So this is some reference. And some results is come from my paper, my last four paper. Yeah. I think I stop here. Thank you.